All right, today we're gonna do. This will be the last section of Laplace. Laplace. Yeah, I made it all the way through and blew it on the last one. This will be the last lecture on Laplace transforms. Um, and so we're gonna do just a couple of examples. We've talked about their usefulness, but now we need to see, okay, what happens when I need to do an initial value problem. So I mentioned before with the discontinuities that you would need that those would that words are hard, that it would come in handy knowing those initial values if you knew it had a discontinuity at a point. So this is going to be, most of these cases will be continuous, but just to emphasize how the initial values play into our Laplace transforms. So one last time, that equation. So big idea, take your ODE, which we're gonna start with a constant coefficients one, and then we're gonna actually change it up a little bit for the second example. But you would transform it, solve it for x, and you would get the Laplace transform of x by doing the components of the derivatives. And then finally taking our inverse Laplace transform to get what our actual solution to the ODE was. So one thing we're going to assume just for these is that our functions are piecewise continuous and of exponential order, meaning they have the Laplace transform. Now, normally we would go on more, but since this is kind of on a time crunch, we're not going to be going into those other methods. So this one's actually a little bit worse than kind of what we've seen before. This is a third degree. So y triple prime plus y double prime plus y prime plus y equals 16 e to the negative t with 3 initial conditions. So to start, just do the Laplace transform of the whole thing. That's going to be our goal. I don't want to have to deal with anything else, so I'm just going to do a Laplace transform. And remember, it was basically these would count down. S cubed y, this would be minus s squared. All right, so where this comes from, remember, this is s cubed y. This is minus s squared times y of 0. Then this is going to be minus s times y prime of 0 minus, you think about it as s to the 0 times y double prime of 0. And then notice here, s squared y minus s y of 0 minus y prime of 0. And you get the picture. And then e to the negative t, that's just a simple Laplace transform. Now our transformed equation is all of this equal to 16 over s plus 1. And here's where it gets messy. Factor out all of your s terms, move over everything that doesn't have a y to the other side, and then divide. Notice in this case it was easier to get a common denominator, or it was easier to go with a common denominator. So now the question is, what do I do from here? Well, factor. That's the best you can do. Factor the denominator. Now, notice this is one of those little things that I mentioned where s squared plus 1, or if it was slightly different, like notice we have an s squared term. Now it's cs plus d, not just over d, because the s squared, you always do one term lower. And then with the multiplicity here, s plus 1 shows up twice, so we have a over s plus 1 plus b over s plus 1 squared, and so on and so forth. Which means, this is why I said you can't always use the heavy side method. S squared plus 1 has no root. Thus, it means I can't find anything for it. Because, or I can't just cancel out that term. Now, I could use -1, but then notice if I plug in -1, if everything were to be multiplied out, the only thing that cancels out A and the CS plus D. So you could find B. So you could find B very easily. Well, not very easily, but easier using the Heaviside method. And so if you do that, and going through everything, A is equal to 10, B is equal to 8, and you would start with finding B is 8 through the Heaviside method, and then you would move on to finding all of these. Let's see, C is -10, and D is 4. So, again, not the nicest thing in the world, but it's just, with time, you could find it. So with all that in place, we now have y equals 10 over s plus 1 plus 8 over s plus 1 squared plus -10s plus 4, all over s squared plus 1. Break it apart. That's going to be your easiest thing to do, is just break it apart. Don't deal with it as anything more than literally the sum of its parts, like I've said before. And so if you do that, this is just a shift of -1, because it says plus 1, so this is t. You could factor it out through linearity. 8t e to the -t, because of this coefficient, because you can think about it as the shift of 8 over t squared, or just the shift of 8 times 1 over t squared. Again, kick the -10 out to the front. You have s over s squared plus 1, which is the definition of cosine. And then kick the 4 out to the front. You have 4 times inverse Laplace transform of 1 over s squared plus 1, which is the definition of sine. So, after all that, you would find that your original function was this. Now you may be going, okay, well, what about the initial values? The initial values were taken care of here at the start when we brought in s cubed y minus s squared y of 0 minus s y prime of 0 minus y double prime of 0. Sorry. So the initial values come into play at the start of your Laplace transform. And if you went through this, you would still find that when at y of 0, you're at 0, y prime of 0 is 2, and y double prime of 0 is 4. So the initial constant, or we didn't have to go through like at the very end of a typical ODE where once we have the general solution, we go through and find the particular solution is built in to this problem. And notice how much more difficult it would have been if we didn't have those initial conditions, because x of 0 or y of 0, y prime of 0, and all that, those would have just been constants that you would have to keep up with. So this actually makes it a lot easier. So now what if we change one little thing? And that one little thing is, instead of y double prime plus y prime, you can already see our issue is here. We now have a coefficient of t, not just a constant. So what's that do to your problem? Well, Laplace transform of y double prime carries on the same. We'll come back to t momentarily. and then Laplace transform of y is still capital Y. That derivative rule is very useful. So Laplace transform of t y prime is negative the derivative with respect to s of the Laplace transform of y prime. So, and again, this comes from your y or sy in 0. So now you're just left with this is equal to negative y plus sy prime. And the reason for that is this becomes a product rule here. So in that case, what we're able to do is do the product rule, and now this negative is just left out front. So now our transformed equation is a little bit different. And the problem is it's not quite like anything we've dealt with before. So if you do the Laplace transform, you get a first order ODE in y. So we've brought it down from a second order differential equation to now we've transformed it to a first order differential equation. So this one isn't as nice. Beforehand, everything kind of just worked out a lot better to where it took a first order, or it would take an equation into just algebra and we could solve that and everything was fine and dandy. This one, Laplace transform will take any degree differential equation with a quadratic coefficient into a second order ODE in y. Or sorry. No, wait, I'm right. Because I said any degree. So transformation will take any degree of ODE with linear coefficients into a first order ODE. The Laplace transform will take any degree ODE with quadratic coefficients into a second order. I lost my English ability. But now, what you notice here is we can turn this into a separable equation. Or not separable, but we have kind of that standard form that we're used to. So to find y, we find the integrating factor just like before. Now, in this case, it's easier just to do the integrating factor of 2 over s minus s, which is not the nicest thing in the world. But remember, the whole point was to make it easier to deal with. So now we get our differential, or we multiply this to every term. We now have our differentials, and then we can do our integration. And like before, we're neglecting the constants, because just with the exponentials and everything in the integration, it's just going to get a little bit messier. But notice now, s squared e to the negative s squared over 2 times y. Then we would get 3 e to the negative s squared over 2. Divide both sides by s squared e to the negative s squared over 2. And you wind up with just y equals 3 over s, which means this is 3 over s squared, or 3 times 1 over s squared, which 1 over s squared has a Laplace transform of t. So all that work for 3t. And we can see if we plugged in 3t, do the first derivative, it's going to cancel, or 2 derivatives of 3t is 0. T times 3 is 3t, minus 3t does get us 0. At 0, the function's 0, and then at 0, the derivative is 3. So all that work just to get to 3t. But it worked, and the nice thing was it took our second order equation with polynomial coefficients down to a first order that we could use the integrating factor method and solve relatively easily. Again, just a lot of algebra to keep up with here. And so that does it for Laplace transforms for this course. We're going to move on. I don't remember exactly what's next because I think I kind of jumped around a little bit, but we'll pick up wherever that ends up to be next time.